All right, ladies and gentlemen, the rest of you. Right now, you are listening to an instrumental version of the Atmosphere. Highly recommend checking out Atmosphere. Anyway, last class on Friday, what we talked about, we began discussing ideal gas theory with the ideal gas model and something called kinetic theory. Some people also refer to this as a topic called statistical mechanics, and it really gets into the beginning of thermodynamics. So let me break that down a little bit for you. Why is it called thermodynamics? That's really the larger picture of what we're talking about. Thermodynamics is a study of temperature and heat. And we will learn about today that heat is not what we typically think it is. We say that things are hot. That's how we describe objects, right? Or things are cold. And those work qualitatively, but when you want to quantify how hot is something, we need better scientific words to describe it. I hope you guys have out your notes from last class. We got through the beginning of that. I just handed out this new packet to you. So thermodynamics is really this very large study of how much energy objects possess and how they change that amount of energy through heat. And we've talked about work before. Last semester we said that work equaled a change in energy. And I think I used a capital E when I wrote this down for work, right? We said work is a change in energy. And that could mean that you could do work on an object and you could contribute to its kinetic energy, or you could give it some potential energy. You're going to see that in this unit, instead of using a capital E for energy, we're going to use U, which we used to mean potential energy before. And now, when we talk about thermodynamics, this is really going to be something called like internal energy. Okay? And internal energy is kind of like, it could be kinetic, it could be potential. It probably would make more sense to leave it as a capital E, but everyone always uses a capital U, so we're gonna go ahead and adopt that convention. Now, the reason why I'm telling you this is because all you're gonna see is that we are going to add on to work. It turns out there's another way to change an object's energy that is different from work. There's a different process that's called heat. Okay? And heat has a math symbol of a capital Q. But the important thing to understand here is that it's like work in that an object doesn't have heat. It's weird to say that. You wouldn't say an object has work. You can say an object can do work, or work can be done on an object. We should use that same terminology when we're talking about heat. We should say an object, okay, that sounds weird, can do heat. An object can absorb heat. An object can emit heat. But an object doesn't have heat. Okay? So it's just kind of a strange way of talking about it. Okay? You can lose heat. There can be heat losses, especially when they played the Warriors earlier this season. There was a heat loss. And then more recently, unfortunately, there was a heat win over the Warriors. But anyway, we won't get caught up on that. So that's thermodynamics. Okay, we're going to talk about these processes, right? These are going to be very different. These are dynamic variables. I'm going to write this right here. Dynamic variables, because they result in change. That change is important. A dynamic variable, what you do is you look at how much energy something has in position A, then you do some stuff to it, and then you look at how much energy it has in position B. And if that energy is different, how did that energy change? Well, you can either say that there was some amount of heat lost or gained, or there was some amount of work that was either done by the object or done on the object. Do you guys remember that we had a couple of problems earlier this semester where we had to deal with those really annoying prepositions? The work done by versus the work done on. Do you remember this? We talk about like just how it changes whether it was a positive amount of work or negative amount of work. These are dynamic variables. To contrast these dynamic variables, we talked last class about some static variables. The static variables were primarily PV and T, pressure, volume, and temperature. Okay. What we're going to do now is we're going to talk about a specific kind of thermodynamics. We're going to talk about thermodynamics as it applies to ideal gases. And in this sense, we're talking about very, very small particles. Okay, and I showed you guys this. Come on. No. How about now? I showed you guys this before. Okay, this is basically what we're talking about. It is studying the study of molecules inside a container. Because gas molecules are so small, it doesn't really make that much sense to talk about one individual gas molecule. It's too tiny. We can't ever just like hone in and look at just one. So instead, we look at the collective amount of this. And just one important highlight here is if you look carefully at these, little tiny molecules, they're all moving at different speeds. Okay? And so we can't really say what's happening to one. One molecule might have a tremendous amount of energy, and one molecule might be moving very slowly and not have a lot of energy. So instead, we talk about large-scale averages. And that's when thermodynamics becomes statistical mechanics. We can't look at just one object. So instead we have to use statistics. And that sounds fancy and scary and crazy mathematical, but we're really just talking about averages. Okay? We're looking at like what happens on average, because one object is too small, too individual. Okay? So if you look at this, there are certain states involved in this. The states would be what's the volume of the container? What's the pressure of the container right now? What's the temperature of the container right now? And when I do certain things to this, there are two specific things that there are three things that I can directly change. I can change the volume by pulling this guy. Okay? So that's changing the volume or pushing it. I can increase or decrease the volume. I can add heat or remove heat to the system with this little tiny guy down here. I can put a flame underneath. It's getting too hot. Or I can put some ice underneath to cool things down. Okay? That's how we add or remove heat to the system. Okay? And you can see what happens. The third thing that I can control is the amount of gas. I can pump this and increase the amount of gas in here. Okay? The two measurements that I cannot directly control, pressure and temperature. Okay? Those are measurements that occur based on all the other variables. Does this make sense so far? I hope this really helps you visualize what we're talking about. Okay, so now what we need to do is, here are the concepts. How do we use it? And what kind of mathematical models do we use to make predictions about what will happen to a gas inside a container like this? And before you think that this is very specific, why are we talking about gas inside a container? Why would we do that? Well, it's kind of the study of, and I think maybe I have an overhead here. Let me just check this. This is very, very useful when you're talking about a heat engine, okay? And I hope to show you, I have a physical heat engine to show you, but it's kind of the way that an internal combustion engine works to power most cars. Okay, that's the same study right here. If you have a 4-stroke engine inside your car, and kind of the way it works, where you look at these different phases of this cycle, where you have, or a 2-stroke engine, where you have, a piston that you're using an explosion of fuel to generate power. You're using heat to create energy. Okay, and that's what happens here, and we'll talk a lot about this and kind of the rules that apply. It's also just fascinating way to think about energy. Last semester we talked all about force and energy, and now we're really going to investigate the specifics of energy a little bit better. Okay? All right, so here's a review of some things we talked about last class. Bam. What makes gas ideal? What is ideal gas? There's a lot of inappropriate flatulence jokes that could be made here, and I'm going to just skip over those entirely. What is it about an ideal gas that makes it so ideal? Well, there's no such thing as a truly ideal gas, but many gases share the same properties as standard temperature and pressure. When we talk about an ideal gas, we make the following assumptions, okay? So this is kind of like last semester we used free bodies, right? We assumed any complicated object was a dot. We're going to assume any complicated gas, hopefully, will be like this. The gas as a whole has volume. It takes up space. But the individual molecules are point particles taking up no space. Most of the gas is empty. This means the gas must be dilute. The gas can't be too dense. That's another way of saying this in simpler terms. Gas can't be too dense. Is this a fair assumption? Not really, but that's okay. Right? Of course the gas molecules, individual molecules, have some volume. The molecules do not experience electrical interactions with each other, just elastic collisions. And just to emphasize, I might even write perfectly elastic collisions. Okay? So I'm going to write, in other words, no ions in the gas. The collisions the gas molecules experience with the wall of the container are also perfectly elastic. Okay? No natural energy loss. Our containers are perfectly insulated when we want them to be. Okay? All gases obey the ideal gas law, meaning that at STP, 1 mole of ideal gas occupies 22.4 times 10 to the negative third meters cubed, or liters, or 22.4 liters of space. Okay? Now, what is STP? What are the conditions for STP? We wrote this down last class. Do you remember? We said that the pressure should be 1 atmosphere, which is also the same as 1.01 times 10 to the 5th pascals. And that the temperature should be 273 Kelvin, which is also 0 degrees Celsius. Okay. Which is also 32 degrees Fahrenheit, but we don't care about that. Stupid Fahrenheit. Okay? And we talked about a couple of super important equations. The most important one is right down here. I'm going to put a box around it, called the ideal gas law. Okay? This is all talking about the math symbols that we use for the various quantities. And we have a couple of key relationships regarding number of molecules and the mass of those molecules. Okay, we even solved a couple of sample problems. And then we have this relationship of constants. So I'm just going to write the relationship of constants. Okay, where we said R is the ideal gas law. R is the universal gas constant, which I wrote right up here, 8.31. Na is Avogadro's number, and Kb is Boltzmann's constant. Okay, and it all has to do with the number of molecules. Okay, good. Just as a little piece of advice, always use Kelvin. Do you always have to use Kelvin? Will you get the wrong answer if you don't use Kelvin? Not necessarily, but you won't ever get the wrong answer if you use Kelvin. Okay, Kelvin's safe. Good? Savvy? Yeah? Down here we talked a little bit about how kinetic energy, how temperature is really directly proportional to kinetic energy. And when you think about high temperature, just think in your mind, it's a measure of how fast molecules are moving. Okay? Good? All right. If you take this and you replace average kinetic energy with what it actually equals, 1/2 mv squared, and then you say, you know what though? V squared we're taking the average values of the v squares. We're taking all the squared velocities of every single molecule, and then we're averaging them at the average kinetic energy. We would also do the same thing for mass, but I'm not going to write the average underneath mass, because we'll assume that we're just using one kind of gas. We're not mixing together hydrogen gas with oxygen gas. We're just using one type of gas. Okay? So there's only oxygen gas, there's only hydrogen gas, there's only nitrogen gas, whatever it is. Okay? And so that's the average, and that equals 3/2 kBT. And if you rearrange this equation, you can cancel out the 2's on both sides, and you want to solve this, and you end up taking the square root of v squared averages. That is called VRMS. And what that stands for is the root of the mean or average of the squares. So the root mean of the squares. It's the root of the mean of the squares. The root of the mean of the squares of the velocities. That's way too many prepositional phrases, but that's what it means. If you see RMS, that's what it stands for. Okay? If you want to sound super smart, you go into a thermodynamics class in college, just make sure you know what RMS is, and then drop that into casual conversation. Oh yeah, well that's the, that works for, it doesn't have to be velocity, but if you need something that happens to depend on something squared, and you want to look at it on average, bam, talk about RMS, the root of the mean of the squares of the values. Okay? Make sense? Maybe not. Here we go, that's the average part, that's why it's called statistical mechanics. Okay? All right, so you can then, you rearrange this, you solve this, you can substitute in and out for various variables. Like if you want it to depend on the molar mass and the universal gas constant, you could use these relationships up here to swap out R. Maybe you don't like the universal constant, you prefer Boltzmann's constant. And you want to use the actual mass. Some books use a mu, some use just a little m. And it says that actually right up here. Okay, good. Any questions about this so far? This would allow us to try to figure out how fast, on average, are the molecules moving. We would figure out the VRMS. Okay, good. All right, so this is just a really good reference sheet for you. Before we go over this page, I just want to go back and I want you guys to solve. And I don't think I asked you to do this on your own, so I want you to try to solve. On your notes, I think we got through the first page. Yep, found it. Okay, we got through this page here, which was from Friday's class. Okay, but we stopped here. And here's a couple sample problems for you. It says, calculate the number of molecules per meter cubed in an ideal gas at room temperature. I'll give that to you in 1 second. Here's what I want you to figure out. First of all, what are the variables for this? Molecules per meter cubed. What mass symbol do we use for the number of molecules? What mass symbol is that? Jamie, you know? Do you need one of these?
Yes, please.
Jamari, do you know what mass symbol we use? Yeah, it's a capital N. And be careful, because lowercase n is the number of moles, capital N is molecules. So we're trying to find N, and then meters cubed, what's that? That's a measure of volume. So we're trying to get capital N divided by V. Room temperature. Room temperature is generally about, do you know what room temperature is in degrees Fahrenheit? It's like what this room is at right now, literally. Do you know what it is?
70.
What the temperature is in here? It
67.
says 69, okay? Or 70 degrees Fahrenheit, which is about, room temperature is about 20 degrees Celsius. We don't like Celsius, we're gonna go with Kelvin. it's really easy to go from Celsius to Kelvin. In Kelvin, this is just 293 Kelvin. So if you take Celsius and add 273, you get Kelvin. Okay. Oh, did I explain that for some reason, we don't say degrees Kelvin. Don't go to college. In your thermodynamics class, if you drop in some very articulate, recondite knowledge about VRMS, and then you ruin it by saying degrees Kelvin, don't say degrees Kelvin. People will laugh at you. And when someone else says degrees Kelvin,
you laugh?
No, be nice. Don't be a physics bully. Don't laugh at people who say degrees Kelvin. Just know that they're stupid, okay? You don't need to say anything. You can just shake your head in shame, okay?
I don't know.
No, I'm just kidding. Don't be a physics bully.
with you.
Idiot.
I don't know.
You say degrees Kelvin? You're so stupid. Don't do that. Don't do that.
But if they're going to do that to us, shouldn't we stand up for ourselves? Okay.
Anyway, so how do you solve this problem? It says ideal gas, right? So immediately you should say, okay, PV equals nRT. Well, that might help us. But also what might help us is saying, oh, you know what I think I left off here? One thing we need to know is how many moles of gas are we talking about? I think I left this out. So let's say there's 1 mole. Okay. You're trying to find N over V. N is equal to the number of moles times Avogadro's number. Okay? And that's the amount of, if you know that, like for example, 1 mole of ideal gas. Now room temperature is pretty close to the conditions for STP. So I'm going to divide by 22.4 times 10 to the negative third meters cubed. And this will at least get us very close to our answer. If it's slightly warmer, it doesn't really say what the pressure is, but let's find out what this is going to be. So if we have 1 mole, and Avogadro's number, probably worth memorizing, even though I'll tell you it's given to you on the AP constants list, as is the universal gas constant, as is Boltzmann's constant. They're listed for you. Times 10 to the 23rd, divided by 22.4 times 10 to the negative third. So how many molecules are there in, we're basically just doing this for STP, calculator.
23rd.
I got a lot. So there are 2.6875 times 10 to the 25th molecules in 1 mole of gas at room temperature, basically at STP. Okay. Let's do the next one. How many moles of water are there in 1 liter? How many molecules? I feel like you guys solve these types of problems in chemistry.
Yeah.
So I don't know if you want a second to try to work it out. I'll give you a clue. Water is also known as H2O. Groundbreaking, I know. Okay. If you want to know this, you should figure out what the molar mass of H2O is. In other words, M for H2O is equal to what? How many grams per mole? Do you remember how we did this? We said H plus H plus O. In fact, we might have done it on the previous page. It equals 18 grams per mole. We are trying to figure out N, right? And they tell us water's density. And actually, we're going to get into this later, but you know in freshman year we talked about the equation for density was mass divided by volume.
Oh yeah.
Yeah.
The broken heart.
I'm just going to tell you now, instead of a capital D, we are going to use, for density, we're going to use a rho.
What?
We're getting more sophisticated, so we're stepping up our Greek alphabet. It's like a P that's got a curly tail.
See that thing?
That's a rho. Okay? So you know what the molar mass is, right? In 1 liter, what's the mass of 1 liter? The mass of 1 liter of water is, let's do density times volume. 1 kilogram per liter, and what's our volume? 1 liter. So we have 1 kilogram of water. And how many grams is that? Oh, come on, give me something. 1 kilogram is how many grams? 1,000 grams, thank you.
1,000.
So now what do? Can you figure out what to do? I told you what the mass of our water is. You have the molar mass. You better be able to figure this out. Think about units.
1 second. I think you do that.
Please solve it. Please figure it out. Go, hurry up. Check with your neighbor. Calculator might help, but you should know what to do.
Yeah.
Just based on looking at the units to be able to solve this problem. We know how many total grams. We know how many grams per mole. What do we do with these numbers?
And there are 6 1, 2, 3, 4,
That looks pretty serious.
Good. There are there's that many molecules in a mole, and you're trying to figure out molecules. So you just do 18.
All right, what do I do? Someone please tell me, what do I do
Times.
to find the answer? Luis?
1,000 divided by 18.
Yeah, you have 1,000 total grams, and every 18 of those grams is 1 mole. And I believe that if you did, basically what we're saying is N equals little m divided by capital M. And I believe that you get 55.5 repeating moles. Okay? What is the ideal gas law? Write it down one more time. PV equals nRT. Okay? Now, if, I'm going to show you some variations of this, which for some reason, people got to name after themselves. If T is constant. Okay? In other words, delta T equals 0. That means there's no change in temperature. How could you do this? You could have a perfectly insulated container so that you could squeeze it or stretch it out and the temperature stays the same. Like it draws in heat when it needs to keep the temperature the same. Keep the molecules moving at the same speed. That's how you can think about temperature. Okay? What you end up with is this. You get the pressure and the volume in the first scenario will equal the pressure and volume in the second scenario. And this is called Boyle's Law. Okay? Have you heard of Boyle's Law before? Good, because you heard about it your freshman year, so I knew you were going to be lying if you said no. We talked about it. Basically, it means you squeeze a balloon, it pops. It tells you that pressure and volume are inversely proportional, but only if temperature is constant. Okay, that's called Boyle's Law. There's another law. What if, and just think about how this makes sense. Please think about how this makes sense. If you want the temperature to remain the same, okay, and you take an object's container and you make it larger, but you want the temperature to stay the same, think about what has to happen. If you want the temperature to stay the same, and you make it larger, the molecules are moving just as fast as they were before. But how is that going to affect the pressure? It's a bigger container. Are you going to run into the walls as often anymore? No, if the volume's bigger, what's going to happen to the pressure? It's going to drop, right? This tells you that pressure and volume are inversely proportional to each other. If you have a bigger volume, you'll have less pressure. One goes up, the other goes down. If you squeeze a container and the molecules are moving just as fast as they were before, if the volume goes down, they're going to run into each other and the walls more often, then the pressure will go up. That's Boyle's law. Okay? The next one is called, maybe I have an overhead for this too. Gas law. Next one is called Charles' law, which says if P is constant, then, so in other words, delta P equals 0. Then V1 over T1 equals V2 over T2. Okay, and this comes from the ideal gas law. Okay? And this is called Charles' law. All of these, by the way, N is constant. All bets are off if you start adding more gas, right? N is the number of moles, so how do you control that? By pumping in more molecules or by taking out molecules, okay? Then there's one more, and this one is P1 V1 over T1 equals P2 V2 over T2. That's called the combined gas law. Okay. That these three things have an influence over each other. Okay. One more weird thing that I'm going to tell you about is an object's triple point. Triple point is a rare feat. It's pretty awesome. It's kind of like a triple-double in basketball, where it's super cool and deserves to be recognized. A triple point. Anyone know what it is? We're talking about phases of matter. Okay, phases of matter, solid, liquid, gas. Anyone have an idea? Triple point? You guys remember talking about this when you were freshmen? What happens to the boiling point of water at higher altitudes?
It goes up.
Is it easier or harder to boil water in Lake Tahoe?
More difficult.
It is easier to boil water. Water begins boiling. Normally water boils at 100 degrees Celsius at sea level. There. But when you're up higher, at higher elevations, it might start boiling at 95 degrees Celsius. Okay? It starts to boil before it gets hot. And the reason is at higher altitudes, there's less air pressure. Air pressure is pushing down on the surface of a liquid, keeping it condensed together, keeping it as liquid. If you remove that pressure, it starts to boil. You could have water boil at 20 degrees Celsius. You could have water boil at 0 degrees Celsius. A triple point is when a material can exist in all three phases simultaneously. And the way that you do that, you create that triple point, is by messing with the air pressure that's on it. You can have ice in water that's boiling if you reduce the pressure enough on it. Yeah. Like in class. You need I don't have a good enough vacuum pump, so you need a vacuum pump. I bet you could probably search for it online. I should probably look it up. Maybe I'll do that later and see if I can find it. Triple point of water. You literally put it inside a container. Usually it's like a large glass jar called a bell jar, and you pump out all the air inside, and then you'll see water boil. And it doesn't mean it's hot. It just means that it's changing its steam. Weird. Okay? All right, calculate the density of oxygen gas at STP using the ideal gas law. You want to calculate density? Means you need to find mass divided by volume. I feel like, the density means that it doesn't matter how much you have. I kind of want to give you a second to try to solve these two problems. Go ahead, I'll give you a minute to try to solve these two problems. Go. Wow. All right, so let's solve this problem. Density is mass divided by volume. Little m. Little m is number of moles times molar mass. Divide that by volume. Volume is nRT divided by pressure. Hopefully you're good at dealing with fractions within fractions. Cancel out the n's. Bring the p up to the top. We got p, capital M, divided by RT. Good news, we know everything here. Okay. The pressure at STP, 1.01 times 10 to the 5th pascals, newtons per meter squared, times the molar mass, which is 32 grams per mole. Down here we have R, which is 8.31, and that's joules per mole Kelvin. Okay, and then we have temperature, which at STP is 273 Kelvin. Okay, if you look at the units, they should all cancel out with and get us down to. Oh yeah, I think we're going to end up with grams. I don't know, we can figure that part out later. But let's do the math. When we solve it, we end up with, oh man, I didn't actually do it. Okay, 32 times 1.01 x.5 divided by 8.31. I end up with 1,424.6 grams per, I want to say it's meters cubed. Okay? Does that sound like a reasonable answer? Which, by the way, would be 1.424 kilograms per meters cubed. Does that sound reasonable? Because we're talking about oxygen gas, right? And guess what? That is very reasonable. Because I will tell you that standard air, okay, 1 meter cubed, think about the size of a box that's 1 meter cubed. The weight of the air inside this box, like if we filled it with regular air, would be about 1 kilogram. It's slightly more than 1 kilogram. Regular air, lighter or heavier than O2? What's most of the air made out of that we breathe?
Different gases.
Nitrogen gas. Like 78% of our atmosphere is nitrogen gas. Is that heavier or lighter than oxygen gas?
Lighter.
Look on the periodic table. Nitrogen is lighter than oxygen. So yeah, nitrogen gas is lighter than oxygen. So it makes sense. Our answer is slightly larger than what I would expect it to be if it were filled with air, which makes sense because oxygen is heavier, slightly heavier than nitrogen. Okay, try this one. A storage tank contains 32.7 kilograms of nitrogen gas at an absolute pressure of 3.8 atmospheres. What will be the pressure if the nitrogen is replaced by an equal mass of CO2? So what we're going to do here is we're going to use the ideal gas law twice. Okay, first let's use the ideal gas law for N2, and then we're going to use it again for CO2. The problem is, in the ideal gas law, they don't tell us, there's no mass included in here, right? So we need to replace, mass comes into play when we talk about the number of moles. So we need to replace our number of moles with the actual mass, because that's what we're given here. So how do you go from mass to moles? And the answer is it's mass equals N times capital M, right? So let's just replace PV equals little m over big M RT. And this side, PV equals M over capital M RT. Okay. Capital M for nitrogen gas. Look at the periodic table, or look at the back side here. I wrote it down. Nitrogen 14.01. Double that, 2 nitrogen atoms, 18 grams per mole. Okay. For CO2, We even calculated on the side, I think. Oh, maybe we didn't. Oh yeah, we did at the bottom. 44 grams per mole. Yeah. I don't know. 28, that's what I meant, right? 28. Right? 14 times 2? Okay, sorry. Good, thank you. What else do we know? We know the pressure. However, it's in atmospheres. Okay? To be on the safe side, we might be able to leave it in atmospheres if we really keep track of the units. To be on the safe side, though, let's convert that into pascals. So 3.8 times 1.01 times 10 to the 5th, because that's equal to the number of pascals in one atmosphere, and that's the number of atmospheres. So our pressure for both, that's the pressure in the first one. $383,800 pascals. Plug that in here. We know that the volume in each of these containers will be the same, right? We're trying to find, our ultimate goal is to find this new container here. So let's figure out, what do we need to know to plug in over here? What's going to stay the same? I think we have to assume that the temperature is going to stay the same. Okay, between these two, we're going to assume that it's isolated. Probably should be more clear on that, but the temperature is going to stay the same. It's the same storage tank, so the volume is not going to change. Okay, does that make sense? And R is not going to change either. This is very useful. What we're going to kind of look at here is anything that's going to change, let's move it to one side. Anything that's going to stay the same, let's move to the other side. Okay, so I'm going to basically put PM over little m equals RT over V. See how I just did some algebra to rearrange this, turn it into a proportion? Brian?
Can you explain how why you multiply the 3.8 times the 1.01 times 10 to the 5th power?
Yeah, it's 3.08 atmospheres, and there's 1.01 times 10 to the 5th pascals in every atmosphere of gas. It's just a unit conversion. Okay, so that we have it written in pascals. We actually, turns out, we didn't need to do that. Our answer in the end, we could have just given it in atmospheres as well, but changing it to pascals just to be on the safe side. Okay? So PM over little m is going to get us 383,800 divided by capital M, and again that's pascals, times capital M, which is 28 grams per mole, divided by 32.7 kilograms. And that's going to equal RT over V. But you know what? Instead of actually doing the calculations here really quickly, let me rearrange this side over here as well for carbon dioxide. Rearrange this equation. For carbon dioxide, I'm going to get, let me use blue, PM over little m equals RT over V. This RT over V is the same as that RT over V. Same container, same temperature, same universal gas law. Gas constant. Okay? If RT over V equals, if A equals B, and B equals C, hello?
Hi.
If A equals B, and B equals C,
Then
A equals C.
very good. So all of this is equal to PM over little m. So on this side we have 383,800 pascals times 28 grams per mole over 32.7 kilograms equals 38,000. Oh, just kidding. P, that's the new P we're looking for, times what's the molar mass of CO2 is 44 grams per mole. And I believe it says the same mass, right? By an equal mass, so also divided by 32.7. what we could have done, we could have even left this M over on the other side because they have the same mass. So that cancels out. And the super complicated equation turns out to be not that complicated. And I end up with P equals 244,236 pascals. Okay? Let's ask ourselves if this makes sense as well. We have this lighter nitrogen gas, and we're going to replace it with heavier carbon dioxide. Same mass of each. What's going to happen if the temperature stays the same? If the temperature stays the same, then the pressure has to go down. Okay? Because this gas is suddenly heavier. If it's heavier, the collisions it has with the walls will be greater, but the temperature is less. Right? You think that it's heavier, but we're lowering the temperature. No, we're not. Sorry, the temperature's staying the same, and this gas is suddenly heavier. Wait a second. Does that make sense? Oh, to keep the temperature the same, the pressure has to be lower. That's how I should have said it. To keep the temperature the same, there has to be less pressure. Okay? Because, another way of saying, if you want to keep the temperature the same, but the mass goes up, what has to happen to the velocity? Temperature is kinetic energy. Okay? To keep the temperature the same, keep the kinetic energy the same. But suddenly it's more massive. So what happens to the velocity of the particles? They get slower. So how's that going to affect the amount of pressure in the collisions? It'll be less. Okay, hopefully that makes sense. I don't know. All right, but there you go. That's our answer. On this side, I told you guys that I already filled this in. What I want to do is I want to skip ahead because I want to talk really quickly about, we did all these things. I want to talk about the laws of thermodynamics for a second. Okay, this is one of my favorite things to talk about. Very weird, very important, very interesting. You said it's cold in here?
Yeah.
Is it really cold? Or is it just the absence
You were studying.
of thermal energy?
I meant to say that there's a really big lack of thermal energy here.
We talked about that as well, that there isn't really talking about coldness. We don't measure cold. We only think of things as being hot or having the absence of energy, right? There's no cold. There's no scale we use to measure. Now you could. You could. We've just chosen not to do that. We decide to keep, we measure how much energy something has, not the lack of energy that something has. Okay, which is just an interesting choice and decision. So here's what happened. Good old thermodynamics. Somebody created the first law of thermodynamics. Rudolf Clausius, Sadie Carnot. Carnot was very important in this whole thing. Carnot was a French military engineer. He worked in the French army. This is around the time of Napoleon. Okay, and what they were developing were steam engines. And they were trying to figure out ways to make the process of converting heat into energy as efficient as possible. That was important. How can we make our steam engines better? Burn less fuel and use that fuel to drive locomotives or to whatever, do some type of work for us. So the first law of thermodynamics is really just a restatement. So this is, and you should write this down, you guys all have this down. It's a restatement of the conservation of energy with a focus on heat. Okay? And then this whole thing was written, they're like, wait a second, before we can even talk about heat, we just need to get to some of the basics of directionality. And that's where the zeroth law comes in. Okay? And I'm just going to write the word directionality. Directionality. Okay? What this means is that hot, and even though I said, I guess I could say cold, maybe I'll cross that out and just write less hot. As we said, there is no such thing really as cold. This is the directionality of energy. Okay? And the zeroth law really says that if If you place two objects next to each other, heat will flow from the hotter one to the less hot one until they're at the same temperature. Okay, that's just the rule. Okay, and if you think about this, hopefully it makes sense to you. And it's not necessarily obvious, even though it's obvious in our everyday experience. If I put an ice cube in my hand, say this ice cube's already starting to melt, and I put it on my hand. The history of human nature has shown that heat from my hand will go into the ice cube and it will melt, right? My hand will get colder because it's giving heat to the ice cube. And the ice will get warmer, will absorb that heat. It has never happened, as far as I can tell, in the history of humanity outside of science fiction. No one has ever taken a little bit of water in his or her hand, okay, to my knowledge, even Jesus, and had that water suddenly become ice. Can you imagine? Imagine in your brain the opposite of the thermodynamic process, right? You're holding water in your hand, and suddenly your hand becomes warmer, and the water becomes colder and freezes into ice. Okay? Think about that for a second. That never happens. Why doesn't it happen? I don't know, it just doesn't. Okay? It also never happens that, gravity suddenly turns into a repulsive force. There's some directionality there as well. Okay? And that has to do with energy and thermodynamics. That's the zeroth law. It sounds weird to think about, right? Can you imagine, though, what if things spontaneously got colder? Cold objects got colder, warm objects got hotter. That's not the direction that energy travels in, which is pretty weird. There's some kind of nature to that. Yeah, Brian?
Didn't you say that two objects when they come in contact, they stay at this temperature?
They achieve an equilibrium, right? They come together. They compromise in their transaction of heat, as opposed to the ice cube example, which is just the opposite, where heat kind of flows in the opposite direction. Okay? Did somebody have a question over there? Jasmine, do you have a question? Marissa? No? Yeah.
I was just wondering if the zeroth law helped develop the Stirling.
That's a really good question. I think so, and I don't think I have I think I used to have an image of the Stirling engine, but we'll talk about engines in a second. And actually, what really helped is the Carnot engine, which is part of the second law. So we'll see if we'll get to that in a second. Okay. So zeroth law is kind of like common sense. It's almost like it doesn't even need to be written down, but it is fascinating to think about this idea of directionality. Okay. First law of thermodynamics says that change in internal energy of a gas equals the change in heat plus the work that gets done on it or that it does. Okay? And I want you to think about this idea of work and heat. If you want to take some energy and turn it into heat, that's pretty easy to do. Okay? The easiest way to think about this with the physics that we've learned from last semester, what was the force that we normally had to worry about taking in energy or removing energy from our system? We call it a non-conservative force. Gravity is a conservative force. You hold an object up in the air, it has potential energy, you release it, you get all of that energy back as kinetic energy, right? So in that sense, gravity is conservative. Its potential becomes kinetic, it's all conserved. What was the non-conservative force we had to deal with last semester? Notorious BOP, we solved those problems. The block on the plane, it was up high, it slid to the bottom. It wasn't moving as fast as it was supposed to because it lost energy because of the force of friction. Thank you. Okay? Friction, non-conservative force, removed energy from our system. If you want to turn work into heat, all you have to do, rub your hands together. You're doing work against friction, all of that friction turns into heat. It's easy for work to become heat. Now, what about the opposite? The opposite is using heat to turn something into work, okay, or to change energy. How do you take heat and you make something move? Engines, there have been engines that have done this for 2,000 years. People have figured out ways to heat something up and turn it into motion. Okay, I have something called Hero's engine, which unfortunately is not set up, but I don't think it'll take me very long to set up, so I'm going to show you that, guys, that in about 15 minutes. called Hero's engine. Hero's engine converts steam into motion. When you heat something up, that steam wants to move. It generates pressure. It wants to go somewhere. If you harness the direction of that, you can make, you can make a motor spin. You can make a fan spin. And if you can make something spin, you can make something move. You could just shoot out steam from a kettle and have it propel something across a classroom. Okay, that's kind of these ideas here. Now, what Carnot came up with was the second law of thermodynamics, which says the efficiency, the thermal efficiency of a heat engine, anything converting heat to work, and I said work to heat is super easy, not heat to work, is equal to the difference in input heat and output heat divided by the input heat. Sounds really confusing, right? Let me write it a slightly different way. You'll see it written like this as well. Efficiency is the hot temperature minus the cold temperature divided by the hot temperature. And I want you to just think about like what efficiency really means. Efficiency is kind of a measure of input over output. Let me find my notes here for a second. How much do you put in and then what do you get out of that? That's kind of what efficiency is just talking about, right? How much do you get in, how much do you get out of that? Let me show you guys, and just so you can take a quick look at the equations in thermodynamics and see how many of these we've already covered and know. We briefly mentioned this one. That's the expansion of solids. We haven't talked about this one yet. That's heat traveling across a solid. So these have to do with solids. This also kind of has to do with solids, the generic definition of pressure. We already know what that is, right? Ideal gas law. We've looked at most of these. We haven't done that one yet, haven't done that one. Here's our equation for efficiency, okay, that I'm introducing right now. All that efficiency is measuring is input over output. Oh, I'm just kidding. Output over input. Okay. For example, if you put in 800 joules into a machine and you get work done 600 joules out of it, how efficient is it? We say 3/4. Really, what we say is a percent. We say 75%. Okay. And here's the brilliant thing that's very bizarre that Carnot kind of figured out, and he realized that no engine can ever be 100% efficient. But you improve efficiency by having really, really hot, a really, really hot heat source. So he basically improved the efficiency of steam engines. He said, you know what, don't just make steam, make the steam as hot as you possibly can. The hotter you can make it, and the cooler you can have some other like cooling reservoir, the more efficient you'll be able to make your engines. But what he figured out is that regardless of the process that happens to turn heat into work, you can never have it be 100% efficient. You can't take all the heat and turn it entirely into work. There's always some waste heat. This is never zero. TC never equals zero. If it did, you'd have a perfect heat engine. Okay, there's no absolute zero. Not only that, scientists at this time began talking about entropy. Okay, entropy is a quantitative measure of, it's sort of like the measure of disordered energy. It's really weird because in my brain, I kind of think of disorder is a weird word. And in some ways, it almost sounds order. So this is very bizarre, but let me give you an example here. Let's take a very basic fuel source. Say you have a piece of wood, and you stick it in your fireplace. Now that piece of wood is considered to be ordered energy. It's lined up, it's ready to burn. You stick it in your fireplace, you light it on fire, you release some of that energy. You could use that energy, a wood stove, to heat up your house, to boil some water, whatever you want to do with it. But as it burns, there's some ash left over. There's some smoke that rises and leaves. What you have left behind is considered disordered energy. You can't ever get this back. A lot of people use this example as well when talking about entropy. Imagine a deck of cards that's brand new. You bought it at the store. And you look at the deck of cards, and inside the deck of cards, it's all lined up. Like all the suits are ordered, 2 through ace, and all 4 suits all ordered up. Then what happens is you throw the cards on the ground. Okay? You release, it's kind of like releasing the ordered energy. Now you can reach down, pick up all the cards, and regain and put them back in order again. But while you are reordering the cards, while you're putting them back into order again, you are exerting more energy. Okay? The idea is you can't ever get back to where you started in an engine. There's no cycle that's perfectly 100% efficient. To move through the cycle, you waste some of your energy. A greater consequence of this, and I know I talked about this your freshman year as well, is something called the heat death of the universe, which is not only a weird and crazy and interesting conceptual idea, but it's also the name of my band. Heat death of the universe is this idea. Right now, there are dense concentrations of energy in our world, in our universe. They're called stars. And what's happening to that energy over time? It is the energy from our sun is being dissipated throughout our solar system. And we use that energy all the time, every day, to provide life on our planet. But the sun is dying. The sun is dying. It's giving its energy, and that energy will never come back. And at a certain point, the sun will be out of energy. And what happens to that energy? Well, we use it in all these forms, right? We absorb energy to warm our atmosphere. Plants use it through photosynthesis to generate sugars that we eat and consume, and then we have. But every single process generates some waste. And we are slowly warming up, not just our planet, we're warming up our universe. And entropy is increasing, meaning that there is some waste heat that's continually happening. The heat death of the universe is the idea that eventually our entire universe will be one uniform temperature. And once everything is the exact same temperature, thermal equilibrium, which you might consider to be a very ordered state. In the words of entropy, it's actually as disordered as possible when everything is the exact same temperature. If everything is the exact same temperature, there's no impetus for life to exist anymore. There's no more directionality. There's no force that's making energy move from one place to another. If everything is perfectly neutral in space and in life, then there's no more activity. Right? And that's called the heat death of the universe. Now you can take this lesson, this idea, and think about it as metaphorically as you want. There are always questions that arise in literature and philosophy like, can there be good without evil? Have you talked about this question before? You've never thought about this idea? Can there be good without evil? You need some kind of relative perspective to appreciate like what's good, what's moral, what's virtuous, without evil, without vice in the world. I'm trying to tell you guys right now that according to the laws of thermodynamics, there cannot be hot without cold. That at a certain point, energy will be level and there will be no more life. You guys are taking this surprisingly well. I think it's a pretty depressing statement. Jamie, question.
So you said it's about the whole universe, one temperature dying, death.
Yeah.
But what about like the world? Isn't the universe like continuously expanding?
Yes, which I think is just also causing that temperature to drop. If you think about like the ideal gas law, the ideal universe law, that as the volume of the universe expands, then the pressure kind of decreases, or at least the temperature drops.
So
right?
The new universe doesn't have heat to give us.
No. It's kind of a weird way to also think about like spatial volume in the universe. That's pretty complex and complicated to think about. But if you just think about the energy is slowly dissipating. We have these large concentrations and they are slowly, dissipating that energy. Question.
So the source of heat in the universe are from stars?
Yeah.
Aren't stars like continuously forming, or are you just saying that they will all eventually just die?
So even in that process, here's the important thing, right? I want you to understand is that you can reconcentrate energy together. Okay? You can do that. Like we do that a lot. As human beings, we are doing that. We are taking energy and we are forming ourselves. Like babies grow, plants grow. And in that process, you are reformulating and reshaping energy, but it takes energy to reshape that energy. and some of that energy is wasted. Okay, that's kind of the idea. It's like you can create new stars, but in the process of creating new stars, you are expending energy to do that. So the net sum is always negative. You always lose energy. You can recreate, stars can reform, but in that process, they are also giving off some of that energy. Yeah?
What if you make the efficiency greater, as in like greater than 50%? Wouldn't the majority of it be no?
Even at 99%, you're still losing a little bit. It's kind of like, you're still losing a little bit of energy. There's a great, like, some people compare it to like when you go into a casino, like the house always wins, the house always has that advantage. But eventually, the energy will entirely disappear. If you always lose even 1% and never get that 1% back, you'll slowly get to the heat death of the universe, but over time, you're eventually going to lose.
So the 99 starts dropping down?
Well, it's just that if you keep multiplying 99 by 99 by 99, 99%, you can try it on your calculator, you're eventually going to get down to 0. Okay? 0.99 times 0.99 times 0.99, it's going to get smaller and smaller and smaller. Less available energy to be used. Okay?
Got it.
Which is pretty interesting. This, as you can imagine, this theory didn't go over very well with people. They were like, oh, thanks. Our world's going to die. There's nothing we can do about it. We're in this game that we are always losing. People hated this idea. At this time, this is like also fast forward like maybe 40, 50 years into like the 1860s. And you have people who are transcendentalists like Thoreau and Ralph Waldo Emerson, who are in this romantic period in American history, who read this stuff and were like, oh, that sucks. Just when we were talking about how important it is to be independent, to be on your own, to formulate your own thoughts. So Ralph Waldo Emerson responded to this. He said, okay, energy tends to disorder, but human thought over time becomes more ordered. And so that was his response, to be like, yeah, you could be depressed about the fact that all these energy processes are dissipating energy that we'll never get back, but the human element, the human thought, human knowledge is becoming more ordered over time. We might be every day closer to death, but we're also closer to enlightenment. Is sort of what we thought. Anyway, if that makes you sleep better tonight. All right, so anyway, going through this, those are your laws of thermodynamics. They're explained probably better and more articulately in your book. Please do read up on this last page. Talks about the zeroth law and the first law again. I'm sorry that there's so much talking today. I do want to show you guys that heat engine. So let's talk really quickly about your homework from the book. So this is Hero's engine. You can probably predict what's going to happen. Here's what's going to be awesome, though. I'm just going to take notes until that water heats up. The water inside this flask, when it gets warm enough, we are obviously putting energy into the system because we are burning gas. Natural gas is being burned underneath the flask. When the water heats up, the pressure inside increases. You probably know this. We're making the molecules faster. The water molecules are moving with a greater kinetic energy. It's pretty hot, as you can tell. It's already boiling. There's not a lot of water in there. Hopefully I have the lid on tight enough. It's supposed to explode. I'm going to be safe, though, because I have these safety goggles. If you see what happens, the boiling water emits steam. The pipes on top are heated, are designed so that they point in a certain direction. And what this is doing, I want to make sure it doesn't tip over, it's generating rotation. We are transforming heat into rotational energy. Pretty awesome, right?
Yeah.
It's just
Yeah.
No, you're right. Wait.
Okay.
Right, your favorite
Right.
camera.
Try it again.
I turned
Oh, was it? Oh.
I turned the heat off, and you see it's slowly fading. Literally, like, this was sort of the idea behind the first cars. I don't know if I can call them cars, but they literally they had these giant, like, cauldrons of water on the back of a cart with wheels. And they would heat up the water, and they would have little tiny ports on the back that would shoot out steam. They were like steam-propelled jet engines. Here are some massive problems with this. One, fire is dangerous, okay? That's first problem. Second, water is very heavy, as you guys know. So how much like efficiency you could get from having a giant container filled with water that you heat up, and steam is also dangerous too, to blast steam out versus like, say, I don't know, having a horse just pull your cart. So it didn't really work out very well. And it took many, many years to have a more controlled type of engine that could, say, propel automobiles. I mean, Hero's engine was around for 2,000 years, but it was hard for it to become very useful, despite the fact that it is pretty awesome looking, right? This is the idea, some heat source. Now, with thermodynamics, we're taking heat and we're turning it into energy, but as you can imagine, a lot of the heat is missing the target. And when I had this thing on, we were also heating up the room. A lot of the heat was being wasted. This is not nearly a 100% efficient cycle. If you could allow for some violations in the laws of thermodynamics, there's this great episode of The Simpsons where the teachers go on strike at school and the kids are at home and Bart's acting all crazy and Lisa is like acting crazy too, and she builds this device and Homer's looking at it and he's talking to Marge like, we need to get these kids back at school, they're going crazy. And Homer's holding this device and it keeps going faster and faster and faster, and he yells and he says, in this house we obey the laws of thermodynamics, because this device, if you could violate the 100% rule, and you could have things continually increase the amount of energy, then there'd be no limit to how much you could accelerate things. You could continuously add energy into a system to make it speed up faster and faster and faster. It would lead to a lack of stability, right? Where these energy could just continuously build upon itself. So anyway, this is all laws of thermodynamics. Really quickly, how do we conceptualize pressure? Would you mind tilting that camera back up at the screen up here? Thanks. How can we conceptualize pressure? How do we measure it? We've already talked about all three of these, but just molecules hitting walls. I'm going to do this really fast, okay? What's volume measuring? Space. Okay, how do we control it? Move pistons, piston up or down. So this is our, here's our gas inside here. You want to control volume, move it up and down. How do we control pressure? We don't. Okay? We don't really control pressure. We control other variables help us control pressure. What's temperature really? Average kinetic energy. How do we control it? Put flame or ice under piston. Okay. Can you do work on a gas? How do you calculate? Is it positive or negative? This is the important part. This is the new part. Can you do work on a gas? Yes. How? Compress it. Squeeze it. You calculate work with this simple equation. Work equals negative P delta V. Delta V is V2 minus V1. Whoa. Why is there a negative sign in front of it? There's a negative sign in front of it because if the volume gets bigger, you take out energy from the system. Don't forget that work is equal to change in energy of gas. If delta V is less than 0, okay, think about what that means. Delta V is less than 0. Think about what it means. Change of volume is negative. What are you doing to the gas?
Increase.
If the change in volume is negative, you are squeezing the gas, right? If the change in volume is negative, it means the final volume is smaller than the initial volume. You are squeezing a gas. Think about that until it makes sense in your brain. It means you are doing positive work on the gas. You are doing work, doing work on the gas. Okay? But if delta V, so the opposite's true as well. If the change in volume is positive, it means you're taking energy out of the gas. Can a gas do work on its surroundings? How do you calculate is it positive or negative? So if you do work on a gas, we call it positive. Okay? How do you calculate is it positive or negative? If gas does work on its surroundings, it's negative. And in this case, delta V is greater than 0, work is less than 0. Work is done by the gas. Okay, so work is negative. One other thing that you can do when you look at this equation, and I'm going to write this in this color here. Work is the area under a P versus V, I guess I'll say curve. And those of you who are calculusly inclined, instead of saying that work equals negative P dV, bam, turn it into an integral. And it's a definite integral from the first volume to the second volume. Okay, if you are not calculusly inclined, then it's the area under the curve. Okay? Lizzie. Depends. It's a heck of a lot easier if it's a constant. If it's not a constant, then you might have to integrate. Okay? If it's a constant, then it just becomes this equation right here. Okay? All right, can a gas give off heat? How do you calculate it? Does this always lower the temperature? Heat, how do you calculate it? Q equals NC delta T. I introduced this equation last Friday, or maybe on last Wednesday, I'm not sure. And this is the tricky thing. Does it always lower the temperature? Not necessarily. Okay, I think we'll stop here. There is one thing I want to talk about. I'm going to hand your homework out to you. I have a packet here that's just reading. And there's a sample problem or two done inside. This reading, and I want you to read about in Gene Colley, our textbook, but this is also part of the thermodynamics chapter in Giambattista. And I wanted to show you something that's a little tricky because it depends on the author's convention for positive and negative signs. I don't want you to just see this first, so I can explain it. I really like the way that Giambattista describes heat, but there's a problem with it. These authors have decided, and I try to explain it here, they have changed their convention for the sign. They have it backwards, which I don't like. They put a negative sign. For us, delta U is Q versus W. And I said, he writes right here, we must agree on sign conventions. Bad news, Giambattista, we disagree with you. They talk about the work done by the system. We have always used work done on the system by something else. I will write in our conventions. Okay? We agree on change in energy and Q, but they just flip-flop their signs for work. Okay? So as you read, you'll see in here my notes that kind of explain this, and there's a lot more about the laws of thermodynamics. Oh, hey, guess what? So there's actually a third law of thermodynamics that I didn't even mention, and it's kind of stupid too. The first law is incredibly profound. The second law is super duper profound. The third law is like, yeah, okay, we know what you're saying. It's impossible to cool a system to absolute zero. It doesn't even need to be a law. Okay, it comes out of the second law. It should just be a part of the second law, but there you go. Okay. Again, I apologize for the massive amounts of talking, but next class we're just going to solve problems the whole time. So, too bad everybody showed up today. Today you should have been absent. On Wednesday we're going to solve problems. It'll be way more interesting and helpful. Here's your homework. It's this worksheet. There are also 3 book problems that I want you to do that I wrote on the top of the worksheet. Okay? Read that packet, answer these questions, tell your neighbor to have a marvelous Monday. Peace out.